Rahul here again from MySlate, and here we will continue our discussion on derivatives. Rules of the algebra of derivatives. What happens when we add two functions? Now here u and v represent functions ux and vx. In short, we are writing them as u and v. Okay. So what would be the derivative of the addition of u and v? Well, as you might have guessed it would simply be the addition of the two derivatives. And what would be the derivative of the of u minus v? Well, it is u prime minus v prime, and we can express the same thing in terms of d by dx like this. Similarly, what would be the derivative of the product of two functions? Well, that is u prime times v plus u times v prime, and we can express that in terms of d dx here. This is the derivative of the quotient of two functions u by v, and of course we already know that this would hold when v is not 0. So wherever you have a denominator, you must always specify this condition, otherwise the function is not defined. And this has a slightly complicated formula. In the denominator you have v squared, and the numerator you have u prime v minus u v prime, and you can again derive this using the basic formula for the definition of derivatives. We will not do that here, but if you follow that formula of derivative being expressed as limit as s tends to 0 of fx plus h minus fx divided by h, you can derive all of them. Okay, let us now look at some other examples. What is the derivative of sine cube x? Now, this can be expressed as composite of two functions, g and h, g of h rather, right, where h is represented, h of x is represented as sine x, and g of h is represented as h cube. And if you substitute, you can get this expression, as you can see. And the derivative of that could be expressed as the product of these two derivatives. The first one is dg by dh. So you take the derivative of g with respect to h, and then multiply it by dh by dx. Take the derivative of h with respect to x. So you can see here that the dh gets cancelled in the numerator and denominator, and what you are left with is dg by dx, which is what we wanted. dg of h is nothing but df. So you apply that to this expression. So dh cube by dh, because h cube is nothing but g is h cube. So you get 3h square, and multiplied by d of h by dx, h is sine x. So the derivative of that is cos x, and then you convert everything in terms of x. So because we have x in the original expression, we should try to get the derivative also in terms of x. So we convert this h in terms of x to get our final answer. Similarly, we have another example here, sine of cos x square, and here we can express this as w of u of v, a slightly more complex composite function, where v is expressed as x squared here, u is expressed as cos of v, and w is expressed as sine of u. And then you might have guessed the derivative of f could be written as the product of these three derivatives, dw by du multiplied by du by dv multiplied by dv dx. And you can see here again that dv gets cancelled in the numerator and denominator, likewise du gets cancelled, and what we are left with is dw by dx, which is the original expression. Okay, and if you use that in this example, you get this. And again, like in the previous case, we convert everything in terms of x, because that's what we have as variable in the original expression. So you convert these u's and v's in terms of x to get the final answer. So this is called the chain rule. So whenever you can express a complex looking function of x in terms of composites of two or more than two functions, you can take these individual derivatives and multiply them. That might be simpler to find.